Welcome to the second part of a brief coverage of approaches to data analysis in experimental and quasi-experimental design. And in terms of a couple of topics, we've already discussed some of the quantitative analyses that a person would want to do or consider doing when planning a study are to estimate their target sample size using power analysis. And once the data are collected in a quasi-experimental design, evaluate the data and get some information, not firm evidence, about the statistical equivalence or similarities between groups that were non-randomly assigned. We have also discussed a few of the listed approaches to analysis for different designs. The two groups, post-test only design, that would probably be addressed through an independent samples t-test. Single group change, that is when you have a pre-post with one group, which would be a dependent samples t-test, and a two-group design when you have both pre and post test, which is what I call the independent samples t-test on difference scores, or the difference in differences test. In this material, we're going to cover the three-group post-test only design with a basic one-way Anova. We're going to look at the post hoc test following rejection of the null using the omnibus test. We're going to look at the three-group design when you have a pre and a post test using Anova, when you have two dependent variables, which is a factorial analysis of variance, and when you have the two independent variables and a pre-test, which is the factorial Anova with a covariate or factorial Anova. So in the data that we've looked at before, we've had a study on fairness in grading. And in the example that I'm going to be looking at now, we have three groups of participants in this study. One group participates in an intervention in which they study fairness practices in grading, particularly among low-performing students. We have a control condition, and we have a group of high-performing students. And note that on the right, where you see the notation, it's presented in a slightly different order than it is on the left. So treatment A would be the low-performing students, treatment B would be the high-performing students, and the control is control. So one question we could ask about this is, how do perceptions about fairness compare among the two intervention conditions and the control? And because you have three groups and no pretest, that is a basic one-way Anova, analysis of variance. So I've run our data on the fairness study with fair post, as you see in these results, as the dependent variable. And looking in, if you look down the column in the SPSS output as the source, our independent variable is study 2 IV. Independent variable is the treatment condition. This is the second study because we started with another study that only had two groups. And so it is the effect of the study intervention on the post-test of fairness. And if we read along study 2 intervention to the right, where you see the F test and significance level, the value for the F is statistically significant at if you have a priori type 1 error rate, or alpha, that would be less than 0.05, or you would just report that the statistic was less than 0.001. The model, by the way, did have a significant test overall. That's the omnibus test, which is the test of the full model that you see on the top line. And the estimate of effect size is R squared, which is 0.37. That is the estimated effect of the intervention as proportion of variance accounted for in the fairness scores by the intervention. That's a fairly large effect. So we can interpret that as the final fairness score was significantly different between groups based on condition, or there was an overall effect of condition. Now, the problem here is that we don't know from this which groups differ from which. We have 3 groups, and we don't know where the greater outcomes versus less outcomes are, which ones have differences and which don't. So for that, we need to go on to a post hoc test. And you only run post hoc tests. Those are tests after the fact. So they're after the rejection of the omnibus null, which we did reject in this case, but we're going to go on to post hoc tests. We're going to use Tukey's test here. There are a number of post hoc tests available. They each have their own uses, but Tukey is the most appropriate for this one, and that is enough to be said. And when you run the Tukey's test in SPSS, what you see are the pairwise contrasts in means. So you see that along the top row, that if you compare the people in the low performing fairness condition to the high performance condition, the average difference is 1.15 points, and the asterisk indicates that's statistically significant. The significance level is less than 0.001. And you'll also see that the confidence interval does not include 0. It ranges from 0.67 points, 0.87 points to almost 1.5 points difference. So that contrast between low and high conditions is significant, as is the contrast between low and control conditions. Some of these tests repeat. The high versus the low is the same value as the low versus high, so we can essentially ignore half of the results here. But the other unique pairwise comparison you have is the high versus the control condition, which is also statistically significant, although the mean difference is small. So you can interpret this as saying that the group in the fair grading for low performing students has significantly higher scores on the dependent variable at the end of treatment than the fair grading for high performing students. And both treatment groups had significantly higher scores on the dependent variable than the control group. So we run the post hoc tests in a one-way ANOVA, following rejection of the overall test that there are differences among the groups somewhere to find out where the significant pairwise contrasts are between which pairs of conditions. Now, we might want to improve this study design by having a pretest. And then we might ask, how do end of treatment perceptions compare when there is a third group? Okay, so we have the 3 groups, parallel intervention focused on high performing students after taking the pretest scores into account. So we're going to essentially control for pretest scores. Those are called covariates. We're using those as covariates. We have a design that's a multiple treatments with control pre and post test, as shown with that notation. And because there is the pretest score that you are going to control for, the analysis is an ANCOVA, analysis of covariance. So if we run the analysis of covariance, you'll see that a new row has been included, reported, which is fair pre, which is our pretest score. Fair post is still the dependent variable. We still have a significant model. We have a significant effect for study condition, and we have an R squared of 38% of variance accounted for in fairness scores related to the intervention condition. So we could say that controlling for pre-existing differences on fairness, the final fairness score was significantly different between groups based on condition. That's controlling, the difference there is controlling for pre-existing differences on fairness. And there was an overall effect of condition. Again, we could follow this with post hoc tests, but I'm not going to demonstrate that here. Now, there may be other questions we want to explore. So we might want to explore whether other aspects of our sample, other characteristics of teachers, in addition to their the condition to which they were assigned, the kind of intervention they received, related to their fairness scores. And one characteristic that we have that's of interest, possibly, and we're going to say that it is, and as part of a research question for the purposes of this demonstration, is the type of specialization, childhood education, adolescent education, or special education. And this is a factorial ANOVA design. So it's factorial in that there are multiple factors, independent variables, that are analyzed with a single analysis of variance analysis. And this factorial ANOVA answers two questions plus one I will go into in a minute. But the first two questions it answers is, are there differences between condition groups? Are there mean differences in the dependent variable related to what treatment condition the participants are in? And are there mean differences among the specialization groups on the dependent variable related to the specialization? Are there differences in the dependent variable related to specialization condition? So if we run this in SPSS, this is the output that we'll see. And we're adding lines. In this case, we have no pretest in my first example here. So it's a factorial ANOVA. We see that we have our study type as one of the predictors, or I'm sorry, our intervention type. That's the third row in the output. And then we have the type, which is the variable name I've given to specialization. And we're not really going to talk about this fifth row yet. That's called the interaction condition. And because it's not statistically significant, the significance level is 0.727, above our alpha level of 0.05. We're not going to worry about it now, and I'll talk about it in a minute. But in this particular data set, the intervention type is statistically significant. However, the specialization type is not. The F is 0.036, and the significance level is above alpha of 0.96. And the combination of the two factors accounts for 34% of variance in the dependent variable. Obviously, the specialization type is not accounting for very much of that variance. So our interpretation of that could be controlling for pre-existing differences. Oh, I'm so sorry. Strike that line. I can't strike it on the video, but this is a case where we are not controlling for pre-existing differences on fairness. So in the box at the bottom, please ignore the first clause. The final fairness score was significantly different between groups based on condition, and there was no significant effect of specialization type. And we call the effect based on either one of the independent variables a main effect. So there was a significant main effect for condition, but no significant main effect of specialization type. And again, I apologize for that first phrase in the box at the bottom. That should be struck from the record. We can visualize this main effect with what's called a profile plot. And this profile plot shows the separate lines for the 3 conditions. So the low condition is in blue, the high condition is in green, and the control condition is in purple. And it gives points along the x-axis for each specialization type. And you'll see that although there are some variances, some variability across specialization types, it's never great. What is the notable thing in here is that the highest scores on the post-test are across the board, regardless of specialization type, for the people in the low performing fairness condition. The lowest scores, regardless of specialization type, are for people in the control condition. So in other words, there are consistent effects of intervention condition regardless of specialization type, and that is called a main effect. So we can proceed to post hoc tests just on the intervention condition. We don't need to really pay any more attention with these data to specialization because it doesn't seem to have any impact on the treatment effect. And again, I'm not going to do the post hocs here. You would probably run a Tukey. It's not really any different from what you saw before. Now, if you add in the pretest, then you're running a factorial ANCOVA, a factorial analysis of covariance, because you're adding in the pretest as a covariate. Covariates are the measured variables that are antecedent to an intervention. Sometimes I call them background variables. They can include a pretest. They could also include demographic variables. They're not really part of a research hypothesis, but they are variables that we know may affect results. So in this case, you see once again that the independent variable for condition, study 2 IV, is statistically significant. We find R squared equals 0.421 for the overall model of the specialization and intervention condition predicting post-test given pre-test accounts for about 42% of variance in post-test. So we might think about saying that controlling for pre-existing differences on fairness, the final fairness score was significantly different between groups based on condition, and there was no significant effect of specialization type. However, we need to look further, because if you read into this closely, on the 6th row, you see study 2 IV times type. And if you look over to the right, you see that that value is statistically significant. The significance level is less than 0.05. So what is that all about? That's called an interaction effect. And in the case of an interaction, the differences between conditions are related to or contingent upon specialization type. It's the significant interaction effect. It's when the effect of one predictor variable on the dependent variable is dependent on whatever group coincides with another factor. So for instance, treatment A only has a positive effect on a dependent variable when the sex of the participants is male. But it has no significant effect when the sex is female. That's called an interaction. The effectiveness of the treatment or the impact of the treatment is contingent on a combination of variables rather than a single one. And in this case, we have this significant interaction. So in the case of a significant interaction, you should not interpret the main effect. The main effect had a p-value of less than 0.05, but that value is actually can only be interpreted in light of other values from the other independent variable. So you just can't interpret it directly. You have to interpret it within groups on the other independent variables, in this case, specialization. So we are not going to talk about that main effect for condition. We're going to talk about it in the context of specialization. And there are multiple ways of approaching the interpretation of the interaction effect, but almost all researchers will at least begin with interpreting the profile plot. So when you have an interaction effect, the profile plot may look something like this. Basically, there's a difference in the slope of the line or the shape of the relationships between the groups that is not likely due to chance. And this is actually a rather hard thing to interpret. Interactions are a little bit hard to interpret, but as I think we've talked about quite a bit, interactions are ubiquitous. So whenever we have enough power to detect an interaction, we may very well do so. Depends, really, obviously. But they do take a little bit of language to interpret, and sometimes they're very difficult to interpret. What we seem to have in this case, so let's start at the simple level. This again is controlling for the pretest, and regardless of certification of specialization, people in the low condition had the greatest post-test scores. And people in the control condition generally had the lower ones, but not in all cases. In the case of adolescent specialization, the control condition and the high-performing fairness condition had essentially equal, statistically comparable post-test scores. The intervention at the high level seemed not to work for adolescent educators any better than no intervention at all would have worked. I'll read the text which says it in a slightly different way. After controlling for pretest, change in fairness grading in the fair grading for low performing students group was greater than in either other group across all specialization types. However, in the fair grading for high performing students group, while treatment was associated with gains for those in CHED and SPED, the adolescent group gained no more than those in control. Note, it never says in this little narrative I put in there, statistically different. The profile plot does not yield significance tests. It is purely descriptive. It is often better just to stick to descriptives. The significant interaction that led us to get the profile plot does demonstrate that some of these differences are statistically significant, but it can be less than simple to find out exactly where these differences that are statistically significant lie. And so at least starting with interpretation of the profile plot is a good way to go. And in this case, what it looks like is that the people in the adolescent group are responding differently to different conditions, particularly that they are not responding to the treatment about fairness for high-performing students. So in summary, when you're analyzing experimental and quasi-experimental designs, some of the things that you should think about in analysis when you're planning the study is power analysis. When you're evaluating the data, statistical equivalence or similarities between groups, and then the following test: the independent samples t-test for 2 groups, post-test only, the dependent sample t-test for single group change, remembering that neither one of those designs is a very strong design, the 2-group pre-test post-test, which is not a bad design, and that's an independent samples t-test on different scores. By the way, you can also run that as an analysis of covariance, and some people would prefer to do that. The 3-group post-test only, which is the analysis of variance, followed up by a post-test, a post-hoc test, if you have rejected the omnibus null hypothesis. The 3-group pre-test and post-test, which is an analysis of covariance, because you're adding in the pre-test as a covariate. When you have 2 independent variables, a factorial Anova, and when you have 2 independent variables and a pretest, a factorial and cova. Bearing in mind that in any case of a factorial Anova, you may have a statistically significant interaction, and then you would want to at least begin to probe that interaction by looking at a profile. I hope this has been helpful and that you enjoy my playlist.